I will be going to discuss is the particle in a ring. Consider a particle of mass m confined to move on a ring of radius r. This system is a variant of the particle in one-dimensional box problem in which the x-axis is bent into a ring of radius r, and this figure shows the movement of the particle in a ring. In this case, the kinetic energy of the circular motion can be expressed as, that is, kinetic energy is equal to L square divided by 2I, where Lz is the z component of angular momentum and I is the moment of inertia, that is equal to I is equal to mr square. Here we are using a more appropriate independent variable for this system, that is, the angular position of the ring can be represented by phi, which is equal to x by r. In terms of phi, the quantum mechanical operator corresponding to the z component of angular momentum can be written as Lz, that is equal to operator Lz, that is equal to minus I h cross dou by dou phi, and therefore L square, that is equal to Lz square, that is equal to minus h cross square into dou square by dou phi square. If the potential energy of the particle is 0, the Hamiltonian becomes h cap, that is equal to minus h cross square divided by 2I into dou square by dou phi square. Then the Schrodinger equation becomes minus h cross square divided by 2I into dou square psi phi by dou phi square into E into psi phi. Notice that this Schrodinger equation is exactly in the same form as that of a particle in a box model. Here there is only difference is in the boundary condition. With the particle in a box, there was discontinuity in the wave function at the walls of the box, because at those points there was discontinuity in potential energy. But in this case, that is in the case of particle in a ring, there is no such discontinuity in potential energy, and hence the wave function is continuous. On rearranging the Schrodinger equation, we can write minus d square psi phi by d phi square, that is equal to 2I divided by h cross square into E psi. Here we are using full derivatives, or d square psi phi d phi square plus 2I divided by h cross square into psi phi, that is equal to 0, or d square psi phi by d phi square, that is plus m square into psi phi, that is equal to 0, where m square, that is equal to 2I e divided by h cross square. Do not confuse the symbol m with the mass of the particle. And this is in the form of a second order homogeneous differential equation with constant coefficient, and the solution for this second order homogeneous differential equation is psi phi, that is equal to a constant e raised to plus or minus im phi, or that is equal to c1 into e raised to im phi plus c2 into e raised to minus im phi. Since we are interested in the real solution, we have to write only the psi phi, that is equal to c1 into e raised to im phi. The Euler's formula, it is a mathematical formula that states that psi phi, that is equal to c1 into e raised to im phi, that is equal to c1 into cos m phi plus I sin m phi. Let c1 be a complex number, that is c1, that is equal to alpha plus beta I. Then psi phi, that is equal to alpha plus beta I into e raised to im phi, that is equal to alpha plus beta I cos m phi plus alpha plus beta I sin m phi. This equal to psi phi, that is equal to alpha cos m phi plus beta I cos m phi plus alpha I sin m phi minus beta sin m phi. Ignoring the imaginary parts, that yields the familiar form of the real solution, that is psi phi, that is equal to alpha cos m phi minus beta sin m phi. To satisfy the wave continuity of the wave function, the wave function must satisfy the cyclic boundary condition. Since psi increased by any multiple of 2 pi that represent the same point on the ring, we can write psi phi plus 2 pi that is equal to psi phi and therefore e raised to im phi plus 2 phi that is equal to e raised to im phi. This requires that e raised to 2 pi im that is equal to 1. This statement is true only if the m is an integer, that is m is equal to, that is the m has the value 0 plus or minus 1 plus or minus 2 etc. And using the equation 9 we can find out the quantized energy values, that is the energy eigenvalues of the particle in a ring, and it can be calculated by using the equation em that is equal to h cross square divided by 2i into m square. Compared with that of the particle in a box, the particle in a ring differ in two aspects in the case of the energy eigenvalues. In contrast to the particle in a box, the eigenfunctions corresponding to plus m and minus m are linearly independent, so both must be accepted. Therefore, all energy eigenvalues except E0 are twofold or doubly degenerate, and E0 is singly degenerate with a constant value. Unlike the particle in a box system, the particle in a ring does not have 0 point energy. For a state having m is equal to 0 and this corresponding to energy is equal to 0, and here the wave function is a constant, therefore psi 0 is a constant. Thus there is no variation in the wave function for a particle in the lowest state of a particle in a ring. This does not violate the uncertainty principle because the particle can be found anywhere in the ring with equal probability, and therefore uncertainty in position is infinite. On normalizing the equation 11, we can find out the value of the normalization constant. It can have the value 1 by 2 root of 2 pi. The normalized eigenfunctions of a particle in a ring are psi m phi that is equal to 1 by root of 2 pi into e raised to im phi. That can be verified to satisfy the normalization, applying the normalization condition containing using the complex conjugate. The mutual orthogonality of the functions in the equation 20 can be verified, and these functions are mutually orthogonal and its value is equal to 0 in the case if m dash is not equal to m. The solutions of the equation 19 are also the eigenfunctions of the angular momentum operator Lz, that is operator Lz into psi m phi that is equal to m into h cross psi m phi, where the value of m is equal to 0 plus or minus 1 plus or minus 2 etc. This is a instance of fundamental result in quantum mechanics that any measured component of angular momentum is restricted to integral multiples of h cross. We have to mention one application of the particle in ring model, that is this plane rigid rotor model, that is particle in a ring model, allows the rotational motion only in one plane. The motion of delocalized pi electrons in a cyclic conjugated system, for example benzene, can be approximated to the particle in a ring system. References: Quantum Chemistry, P.K. Prasad, New Age International Private Limited, Introduction to Quantum Chemistry, A.K. Chandra, McGraw-Hill Education India Private Limited, Quantum Chemistry, Donald A. McCurry, Viva Books Private Limited, New Delhi.